0.35 plus or minus to 0.76. 2% of microalgae PHP and cornstarch blending is with glycerol of 4% is slightly opaque and its tensile strength is 1.28 plus or minus 0.10 and elongation break is 1.22 or 4.87 and ends module is 14.67 plus or minus 2.43. According to this result, the concentration of starch increased, the tensile strength also increased. The highest tensile strength is we can observe 1.28 plus or minus 0.10 MPa and 0.86 plus or minus 0.21 MPa in second and 0.54 to 0.12 megapascals was produced. The elongation at break contradictions the data of tensile strength. It will depends upon the tensile strength. It was discovered that increasing concentration of cornstarch what we used here is reducing the elongation of break. This is due to the interaction between starch molecules and reduction of the cohesive force between the polymer chains of PHB, which means we extracted from microalgal PHB. The ends modules increased when the concentration of starch and PHB increased. Present studies also observe that a higher concentration of starch and other lower concentration of moisturizer, the higher metal stiffness and rigidity were observed. Blending with polyhydroxide with cornstarch creates a bioplastic that balances PHP strength and biodegradability with the starch cost effectiveness and processability. This synergy opens up the ranges of practical application of food packaging, biomedical devices, and agriculture products, and many other industrial applications. If we observe the images, we can clearly see the opaque nature in last two images and transparency in first images means 0.5% PHP and cornstarch with 2% glycerol, and the slightly opaque nature in 1% PHP and cornstarch with 3% glycerol and 4% glycerol of last two images. Coming to the conclusion, in current study, it can be asserted that the physical and chemical properties of microalgae PHP and corn-based bioplastic films have been optimized with various concentration of cornstarch and microalgae PHP and glycerol. A film with desirable physical and mechanical properties can be produced with manipulation of concentration of cornstarch and microalgae PHP with glycerol. In comparison of 2% and 4% of concentration of glycerol, corn-based bioplastic films with 3% glycerol had most ideal mechanical properties. This was based on the result of measure parameter closest to the standard value. Standard value is nearly 20 MPa, 20 megapascal as a PP and PVC plastics. Films with composition of 1.0% PHP and cornstarch had most optimized results compared to 0.5, 2.5%, 2.0% PHB concentration. Films made with least amount of glycerol, like 2%, and the most amount of PHP and cornstarch had the high tensile strength and stiffness but lacked flexibility. The properties of an application of microalgae PHP and corn-based bioplastic can be mixed with optimization of cornstarch and glycerol's contents. Thus, the aim of having a target application of bioplastic, the concentration of starch and glycerol can be adjusted for better results. Furthermore, the addition of fillers need to be added. Like here, I've used only glycerol as a filler. We can use the sorbitol and a peg for better product. To enhance the property of PHP with other corn-based bioplastics. I would like to acknowledge and give my warmest thanks to Sri Padmavati Mahila University and my Department of Microbiology. I would like also give special thanks to Iconbet International Conference and coordinators who give the best platform to explore. And these are my references. Thank you.
Okay, thank you very much, Ms. Leela, for your presentation. I would like now to open the Q&A session. If you guys have any question, feel free to ask. Maybe I can start first. For your sample, PHP, we do have PHP for industrial grade. How will you compare the PHP for industrial grade with your sample?
It was my PHP. I need to take this microalgal PHB and industrial PHB will be different, ma'am. It will be degrade easily when you compare it to industrial PHB.
Okay, it's better in terms of degradation compared to the industrial PHP, yeah?
Yes, ma'am. It will degrade fast and it was in a natural carbon compound. So we can take this PHB from microalgae intercellularly. It produces PHB intercellularly. So we can obtain microalgae PHB to intercellular. It will be sustainable. It can degrade easily, faster than industrial PHB.
Yeah. So we have another question from Dr. Zubaida. Based on the physical appearance of the bioplastic film with varying PHP starch glycerol ratios, as shown in the images, what visual differences can be observed, and how might these related to the application suitability?
Actually, this transpiration, we see last three images. The first image was slight transparency, high transparency, and last two images slightly opaque in nature. These transparency will be used for the medical applications, ma'am.
Oh,
Medical applications in the medical.
Okay, so every single one, or difference
Yes,
in
we
terms of
can
the
use.
opacity?
For this pond-based starch, we will especially use it for agriculture because we use mulching covers in agriculture fields, right, ma'am, to protect from air and wind from crops. These mulching covers from pond-based, starch-based will be degrades fast in the soil, and it doesn't contaminate soil pollution, ma'am. It doesn't affect on soil pollution. So we can use this pond-based PHP biofilms for agriculture purpose more efficiently.
Okay, I guess thank you, Ms. Leela, for your presentation. I think we move on to our second presenter for today. I would like to welcome Dr. Farah Cleopas from UMS to deliver her presentation. Doctor, we cannot hear you. Dr. Farah, I cannot hear you. Okay, now I can hear you now. Oh, I see. Okay, never mind. You can play. We did not hear anything from the video. I can hear your voice, but I cannot hear anything from the video.
Okay, at the setting, you need to share with sound.
Good day, everyone. My name is Farah Cleopas from Universiti Malaysia, Sabah. Together with my co-researchers, I'm pleased to present our study titled Potential of Mango and Papaya Seed as Natural Coagulant, which explore the use of fruit waste in sustainable water treatment. To begin with, coagulation is a chemical process where the coagulants are added to raw water to destabilize suspended particles. So these particles, which normally repel each other due to electrical charges, begin to clump together once their charges are neutralized. So these form tiny aggregates called microflocs, which can then be grown into larger flocks during flocculation and removed through sedimentation and filtration. Now, in a typical water treatment plant, coagulation is one of the first critical steps after pre-screening. So it plays a key role in removing fine suspended solids, natural organic matter, and even microorganisms that are too small to settle on their own. So by promoting floc formation early in the treatment process, coagulation improves the efficiency of the downstream process like the filtration and disinfection. So why do we use coagulants? The purpose of coagulant is to enhance particle removal by neutralizing charges on colloidal matter. This is not only helps improve water clarity and reduce turbidity, but also reduce the formation of harmful byproducts when disinfectant like chlorine are later applied. So in short, coagulant make the entire water treatment process more effective and efficient. Traditionally, chemical coagulants are widely used in treatment plants. So these include aluminum sulfate, commonly known as alum ferric chloride, polyaluminum chloride, and synthetic polymers. While they are effective, their long-term use raises several concerns. So this range of from the generation of chemical sludge to potential health risk if not handled or dosed properly. As a sustainable alternative, plant-based coagulants are now being actively explored. They offer several advantages like they are biodegradable, cost-effective, safe for human, and environmentally friendly. So in addition, they often utilize agricultural waste, making them more accessible in rural or low resource settings. So example for plant-based coagulants include Moringa oleifera, Jatopra curcas, tamarind seeds, and in our case, the mango and papaya seed. So the main objective of this study is to evaluate the turbidity removal efficiency of mango and papaya seed extracts, specifically observing the effects of particle size and sedimentation time. Now let's look at the methodology. The unwanted plant parts was removed by slicing, cutting, and scooping, and the seed were first washed, dried, and ground. The seeds were then saved into two sizes, 250 micrometer and 600 micrometers. Next, we conducted jar tests using various dosages ranging from 20 to 70 milligram per liter. And we also monitor 4 key water quality parameters throughout the treatment, such as the turbidity, pH, dissolved oxygen or DO, and total dissolved solid or TDAs. Now let's move to the findings. First of all, we began our assessment with visual observation of the treated water samples. So these initial steps allow us to quickly evaluate the physical appearance and sensory qualities such as color and odor, which are important for user acceptance. So from this observation, we found that mango seed treated water was generally odorless but has slight yellowish tint. Meanwhile, the papaya seed treated water appeared clearer and more visual appealing, although it carried a mild papaya smell. For mango seeds powder at 250 microns, we observed promising turbidity reduction results. So after 30 minutes, the turbidity was reduced by 57 to 76%, depending on the dosage. Even within just 30 seconds, we already saw a reduction up to 57.6%, showing quick coagulation action. So at a dosage of 20 milligram per liter, turbidity dropped from 12 3.7 to 3.04 NTU, which is 76% reductions. However, when the higher doses like 60 and 70 milligram per liter were used, the reduction was slightly lower, around 57 to 60%, suggesting that the overdosing may reduce efficiency. For mango seeds at 600 micron particle size, the overall turbidity reduction ranged from 62 to 68% after 30 minutes of settling. So in the first 30 seconds, the turbidity reduction started lower, between 10% to 56%, depending on the dosage. So at 20 milligram per liter dosage, turbidity decreased from 14.2 to 4.58 NTU, showing a 67.7% reductions. So when we increase the dose to 60 and 70 milligram per liter, turbidity reduction remained consistent between 62 to 67%. So for the papaya seed at 250 microns, turbidity dropped by 47 to 68% after 30 minutes. So in the first 30 seconds, it reduced by around 38 to 44%. So at 20 milligram per liter, turbidity went down from 13.4 to 4.32 NTU, around a 68% drop. So higher doses like 60 and 70 milligram gave slightly lower result between 47 and 57%. So for papaya seed at 600 microns, we observed the highest turbidity reduction among all the samples. So even in the first few seconds, it started to show clearly improvement. And after 30 minutes, the water clarity was significantly better. At both low and higher dosage, this particle size consistently performed well, making it the most effective option in our study. Comparing all results, we found that papaya seed at 600 microns gave the best overall turbidity reduction, especially after 30 minutes of treatment. Mango seeds at 250 microns, on the other hand, show faster initial result, working more quickly in the early stage of the treatment. At a moderate dosage of 20 milligram per liter, both seeds were effective, although papaya required more time to reach its full potential. So when we increase the dosage to 60 and 70 milligram, papaya still performed better, while mango performance remained stable but slightly lower. Overall, mango show a faster reaction, but papaya provide more consistent and higher turbidity removal, especially over longer contact time. So in terms of overall water quality, the pH remained within a neutral range of 6.5 to 6.9, which is favorable. Dissolved oxygen also shows a slight improvement, reaching up to 3.34 milligram per liter. And TDS level increased slightly. Now let's summarize all the findings. During the 5 minutes sedimentation phase, the 600 micron particles show better performance than the 250 micron ones. So moreover, the papaya seed powder performed better than mango in forming early stage blocks. However, we also observed that overdosing with finer powders caused stabilization, which reduced the turbidity removal efficiency. When extending the sedimentation period to 30 minutes, small trend become more evident. So papaya seed powder at 600 micron achieved over 80% turbidity reduction consistently across all dosages. On the other hand, the 250 micron particles show a decline in performance as the dosage increased. Meanwhile, the mango seed coagulants were found to be less effective overall and in some cases left a yellowish tint in the treated water. So to conclude, papaya seed powder at 600 microns demonstrated the most effective and stable performance as natural coagulants. However, its performance, as with mango, was clearly influenced by both particle size and dosage. Given its availability and efficiency, papaya seed coagulant is especially promising for rural and decentralized water systems. That said, that some post-treatment polishing steps may be needed to address the minor sensory issues, especially color and odor. Finally, we would like to acknowledge the financial support provided through UMS Grant SDK 0268-2020, and special thanks also go to our collaborator at RUAS, the Rural Water Supply Living Lab, and Enviro LL, the Environmental Science Living Lab, for the contribution and technical support throughout this project. These are the reference, and thank you very much.
Okay, thank you very much for the presentation. Unfortunately, Dr. Farah cannot be with us for today. It will be interesting to know what other fruits that are still available or to be coagulant. However, can we share? We will be sharing her emails. If there's any further question, we can email her. So moving on to our next presenter, I would like to invite Dr. Nurzaida Zahari, also from UMS, for her presentation. Whenever you're ready, Doctor. I would like to invite Dr. Nurzaida Zahari. Well, I cannot see Dr. Zaida Zahari on the list on our attendant at the moment. Will be okay if we continue our session with the next presenter, Dr. Nur Azlina Alias from UPM.
Yes, sure.
Thank you. Whenever you're ready, Doctor.
I just want to check, are you able to see my slide on the screen?
Yes, we're able to hear and also see the slide.
Okay, I'll proceed now. All right,
Okay, thank you.
Assalamualaikum warahmatullahi wabarakatuh and very good afternoon. I am Azlina from Universiti Putra Malaysia, and today I'm going to share with you on our recent study on one of the polluted lake nearby the Universiti Putra Malaysia. So our intention is actually to evaluate the fabricated biofiltration system for enhancing the lake water quality for lake restorations. So my slide is not moving. Is it? No?
Still on the first page.
It's not moving. So same problems reoccur.
Okay, it's introduction now. Maybe it's a little bit lagging.
Right. So I have to click on the arrow. Is it?
Um,
Yeah.
Maybe.
It's moving now. It's moving
Yes,
now.
it's moving now. Yeah.
All right. So it is well known that lakes globally face degradation due to the anthropogenic activities, or known as the common word is human activities lah in the surrounding. And these anthropogenic activities could be the form of first the industrial discharge, where the mining industries or textile manufacturers industries that they releasing the wastewater contains chemicals, heavy metals, or other organic pollutants directly into the rivers. And then second, it could be due to the solid waste dumping, and illegal solid waste dumping like the household waste, construction debris that directly dump into rivers or nearby the riverbank, which then being washed directly into the river. And then the third anthropogenic activities could be due to the runoff, either urban or agricultural runoff. So the rainwater flows over impervious surface, over the pavement, the parking lots, or roofs. The picking up all the pollutants and convey it into the rivers. So pollutants such as oil, grease from the vehicles, or the pets waste, those directly discharge into the storm drain and then into the rivers. So for the agricultural runoff, rainwater flows over farms carrying excess of fertilizers, which rich in what do we call it, nitrogen and phosphorus, and also the pesticides, and the animal waste directly into the rivers. So this is also anthropogenic activities that may pollute the rivers. And last example of anthropogenic activity is the discharging of untreated or inadequately treated the wastewater from the houses lah. So from toilet, shower, sinks, that is directly flowing into the drain without proper treatment, or there is a treatment but from a faulty system lah. So those anthropogenic activities may lead to eutrophication, which worsening lake water quality. So this eutrophication is a process where excessive nutrients, nitrogen, phosphorus from agriculture runoff, excess from industrial discharge, and inadequate treated sewage, those foster growth of algae and also aquatic plants, which later increase the suspended material and also organic matter in the lake, which eventually results in higher turbidity. So we know that generally the impact of higher turbidity in water body produces toxin.
You elaborate on the dust. What kind of dust and what is the function for the dust?
Okay. Okay, the second question.
Okay, and then for the second question, how did you determine the levels for each of the variables in the Taguchi design?
The what? The what?
The level. I mean,
Oh, the level.
yeah, the level, like for the optimum level, right? How did you decide for each of the
Okay.
I think the ingredients that you use?
Okay. Thank you for the questions. Okay, we have two questions here. Okay, first, the dust. Okay, I'm sorry because yes, the dust. I think I'm not told deeply enough about the dust. Actually, this is the project from the agarwood project. Okay, from the agarwood project. So from the agarwood, we extract the agarwood. The first thing we extract is the agarwood essential oil. Okay, and then we have the waste from the agarwood, which is the white wood. Okay, the white wood. So the white wood we bring to the laboratory. We make it to the dust. Okay, to the dust. So this dust, agarwood dust that we get from the lab, we add in the soap, okay, to give the sensory effect, okay, sensory effect to the soap. Okay, that is for the question number one lah. So for the question number one, we use the agarwood soap. Agarwood dust. Okay, agarwood is pokok gaharu lah kalau dalam in bahasa Malaysia. Okay, I hope that answer the question number one. And then for the question number two, for the level here, okay, to determine the level we use in Taguchi, first what we must do, what we do, okay, what we did, we find the previous journal, any formulation from the previous journal, okay. So let's say we obtain one formulation for the previous journal, and then we need to create a upper boundary and lower boundary. Let's say for the water volume. Okay, the water volume we find in the previous journal, okay, is 80 milliliter. Okay, and then we want to see the effect. What if I added the water volume? What if I decrease the water volume? So we create the upper boundary. We add another 10 milliliter. Okay, so this boundary you may justify yourself. Okay, 90 milliliter. For the lower boundary, okay, we decrease by 10 milliliter. We create the boundary by ourselves. It same happened to the light concentration. Okay, we find any previous work. Okay, we determine the 17 gram. The past researcher used the 17 gram. So to using the Taguchi, okay, if we want to use Taguchi, we must create the upper boundary and we must create the lower boundary. For this research, for the light concentration, okay, our team use 2 gram for the boundary. So that means 2 gram increasing and 2 gram decrease. Okay, that's the way we set up the level. Okay, in the Taguchi design analysis lah. So I hope that's answer the question number 2. Is it okay, Doctor?
Okay, I think that's answering my questions. If you have another time for one more question, if that's okay.
Yeah, we have
Okay.
final one maybe.
Okay. I realized that you have a low R squared value for the antimicrobial activity, right?
Yes.
So why do you think it happens? And then how do you plan to improve the predictive strength for the models to improve the antimicrobial activity?
Okay, thank you, Doctor, for the deep question because this is further research. Okay, I think that actually for the microbial activity there is effect. Okay, from the active formulation. Okay, from the active formulation that we run, there are effects, but the effect is very small. Okay, the effects are very small. So the result is ascribed. Maybe to increase the antimicrobial activity, we need to add another element of the soap. I don't know what is the element that appropriate that we need to add in the soap. Maybe alcohol or sanitizer, something like that. Okay, to create the microbial effect on the soap, something like that. And then after that, we can test it again. Because our soap is just have the this parameter, type, water, lye. Okay, because of this only parameter, it do not possess the microbial element on that soap. Okay, to study further, maybe we must add something element. Okay, some element that may use the that may have the microbial elements. Okay.
Okay, to conclude, it's not the limitation of the Taguchi method, but it's actually the formulation
Yes.
itself. That,
Yeah, the source itself, I think.
Okay, all right. I think with that question and answer, we have to come to the end of our session for today. We would like to see all of you tomorrow to join us again. I would like to invite everyone to kindly turn on the camera for us to have a photo session. Would that be okay? Okay. I'll take. Okay. Is there more? Sorry. Bear with me for a second. Sorry, can you guys bear with me again for a minute? This is quite new for me to take the photo. I take another one with a different view. Okay, thank you very much, everyone. We would like to, we hope to see you guys tomorrow for our final day for tomorrow. Thank you, everyone.
Okay, thank you, moderator.